Okay, hello everyone. Welcome back to Deep Learning Systems, Algorithm and Implementation. I'm TQ Chen. Today I'm going to work with everybody to talk about our lectures on neural network library abstractions. So up until now, we have talked about a few of the basic deep learning models like multi-layer perceptions, as well as the basic automatic differentiation algorithms. Hopefully, now you have started to work on your homework one and having fun building some of these automatic differentiation libraries. Today, we're going to talk about how we can compose the things we build to really form an end-to-end neural network or end-to-end deep learning library. Until now, when we talk about the needle library, the only thing we built so far only contains basic elements like tensors and automatic differentiation. And there are a lot of things we can build on top so that we can build different kind of machine learning model more easily. And today's lecture is going to contain two parts. In the first part, I'm going to quickly describe and discuss with folks on possible programming abstraction we can use to build machine learning models, and actually do a bit of history review of the history of deep learning frameworks. And the second part, I'm going to work with everybody on study some of the high-level modular components and how we can effectively decompose machine learning library design onto different architectural components that can then organically work together. Okay, let's start with the first part. So what is programming abstraction? So the programming abstraction involves things like the API we use to define computations, how we can extend the overall framework to support things like different kind of GPUs and different kind of models. If you have used library like PyTorch or TensorFlow or library before, some of those design choices may seem very obvious for you after you have seen and used them for a while. But if you try to let's try to time rewind and try to travel back to the time where those deep learning libraries are not yet available, and you can find that some of the choices may not become as obvious. And it's very interesting to see how the deep learning framework abstraction evolves over time. It's also important to recap and learn through this thought process on how we eventually arrive at the interfaces we are today, because that helps us to know why the abstraction is designed this way. And also, as the field of machine learning and also machine learning framework evolves, there's always a need of designing new capabilities, and as a result, there are new lessons. These lessons can be used to help us to design new abstractions in the future as well. Okay, and so in the first part, we will do a case study of effectively the history of deep learning framework development, and we are going to specifically focus on three past frameworks that are representative in the history of deep learning framework development. So the first framework we are going to look at is Caffe 1.0. So this is one of the earlier popular framework that help us to do most of the computer vision tasks on GPUs. And even today, it's still being used in quite a few use cases. Of course, most of the use cases have been switched to the later generation frameworks. The second framework we're going to look at is TensorFlow 1.0. And this is specifically interesting when we look at the particular design choices that comes into the TensorFlow 1.0 design. And finally, we're going to look at PyTorch, or today when we're looking at the library like Needle, the programming abstraction we are building really is mirrors what PyTorch is doing. So these three frameworks were quite popular and dominates the market for a period of time in the history of machine learning frameworks. Of course, there are many frameworks being developed along the way that besides these three frameworks, right? So for example, there's earlier pioneer in the field, Ciano and Torch 7 in Lua. And there's also a framework I was involved in called MXNet. Caffe had a second generation framework called Caffe 2, Trainer, and more latestly, there's a very exciting development from Google that leads to JAX. So due to time, we will not study all the frameworks, but a lot of them also share some of the similar traits, and we will mention them as we do the case study. And if you are more than interested, you should go ahead and check out those frameworks as well, and think about, what are the design choices in those frameworks? Specifically, how do you design the interface to build neural networks, and how are they different from each other, and why they come down with this kind of design? Okay, so as a first step, let's first take a look at Caffe 1.0, and it's a typical representation of a first generation deep learning framework. So in 2014, the 2014, the image Alex Strajewski and Geoffrey Hinton and Ilya won the first, using the neural nets to won the ImageNet challenge, right? So that's the inception of the deep learning wave in computer vision, and later on, it's all were different kind of applications. And one of the earlier pioneers there is this framework called CUDA-ConvNet that Alex Strajewski built to effectively allow us to go ahead and compose neural networks and use that for end-to-end training. And Caffe is a system developed in Berkeley that tries to effectively formalize some of the engineering approaches, and then go ahead and allow us to build different kind of machine learning models. They have become very popular, and almost, I think, 80% of the deep learning workload then actually uses Caffe. So of course today it's no longer being as widely used, but it's very interesting to study the interface of the first generation deep learning framework. Specifically, on those frameworks, there is one core abstraction that being used, which is called layer. So of course, in Caffe, the layer is implemented in C++, but I'm just using Python pseudocode here to show the general idea. So when we are composing neural network together, we will always talk about, hey, there's a linear layer followed by a ReLU layer, and then there's a softmax. So you can find that layer is kind of like the basic element that you can use to compose them together. And this compositionality is really helpful, so that, for example, I can not only develop a ReLU neural network, but we can replace all the ReLU activations by, say, sigmoid activation with a few lines of code, and then that new neural network can be trained in the same fashion, right? So a layer interface defines two key functions. The first function is what we call forward function. In the forward function, what it tries to do is try to take data from an input, in this case, it's called bottom, and try to propagate the data and the computation to the output. For example, if my layer is an exponential layer on the left, what it tries to do is it will do bottom exponential, and we are going to assign that to top here. And in this case, both top and bottom have the memory already pre-allocated. So effectively just run a computation and copy the data onto the top. Of course, this is only running a forward computation. In order to compute the updates, we will still need to do the gradient computations and set the weight onto and set the weight gradient and use the weight gradient to do the update. So that's where the backward function comes in. And usually in Caffe, so the top contains the gradient from the output, and there's a propagate down field that uses to indicate, whether or not we want to propagate a gradient to the input. Because if, say, I'm V1, you don't have to propagate gradient. You don't have to propagate gradient to the input, at least in this case, because unless you are doing things like neural style, where you are taking gradient with respect to input. So this is a kind of propagate down. It's just a specific flag that helps us to do certain optimizations. And bottom is the contains the array that allows us to propagate gradient onto. Of course, in the backward function, it's also going to refer to some of the activations and data from a forward propagation. So when in a backward function, for example, if you are doing things like exponential, ideally what you are going to do is effectively you are going to say my bottom gradient is going to equal, in this case, I do have a top value, which is exponential, times the top gradient in here. That is the gradient of exponential. So one thing you'll notice is that in this interface, we are effectively doing backpropagation in place. So for this computational graph, for example, there will be multiply layer, add layer, exponential layer in here that composes together in this way. And then in the neural network training, first of all, we're going to iterate over all the layers, call forward to in topological order so that you will be able to get all the intermediate activations. And then we are going to do reverse topological iterations and call backward function to propagate the gradient back. After that, each of the layer will contain the gradient with respect to their internal weights. And then we can call sometimes the update function or solver function to take the gradient and the weights and update the weight in place so that we can get effective weight updates. And in the next iteration, we're going to do that again. So if you look at this interface, right, you can find that it's slightly different from what we talk about in our automatic differentiation lecture. Instead of taking the computational graph and extend another computational graph that performs the gradient calculations, it simply builds up the layer interface and propagate it in place. So what are the advantages and disadvantages of this layer interface? Or another question that I want everybody here to think about is why did the author of Café and CUDA-ConfNet come up with this layer interface? Well, right now, if you look at the design choices, maybe it seems not as obvious to you because you are getting more used to the computational graph automatic differentiation anyway. But if you don't imagine that you have not learned about any of those concepts and you just learned about the forward propagation and back propagation in deep learning, very likely you are going to come up with some interface that looks like this one because it's quite natural, right? You get layers, and each of the layers you can do two actions. You can do forward propagation, and then you can do backward propagation to get a gradient. I personally also developed my own libraries at the time, trying to work on some of the deep learning workloads, and I also come up with a similar interface that contains a forward and backward function. So it's kind of a quite natural choice. And if you look at the description of backpropagations by Gavin Hinton and others, initially you will find that it's also a quite natural choice to end up with in the beginning. So this style of interface kind of become popular and become the standard of the first generation of deep learning framework. So after 2015, you'll find that there's a second interface, which is a TensorFlow interface that start to have the concept of computational graph instead of layers, right? So the difference of computational graph and layers is that in the computational graph, we are simply describing the forward computations. And then when we're taking gradient, we are going to extend the computational. And so TensorFlow is a typical representers of this style of API, and specific TensorFlow 1.0. So if you talk about TensorFlow now, it's already at 2.0. So a lot of things have changed, and the TensorFlow have already also adopted some of the imperative programming APIs that PyTorch uses. But we're going to focus on the TensorFlow 1.0 API because it kind of represents a a very interesting way of designing programming abstractions for machine learning. I also want to mention that actually TensorFlow 1.0 is also not the first framework that come up with the concept computation graph. It's only pioneer called Ciano from University of Montreal, and the concept of computational graph actually was pioneered by Ciano. So a lot of you can see quite a few reflections of the API design between TensorFlow and Ciano in the early days. Okay, so let's take a look at how we are going to take a deep learning model and try to describe that using the computational graph API in TensorFlow 1.0. And let's walk it through line by line. So to describe a computational graph, first of all, we are going to create a variable in here corresponding to v1, which says, this is the in-place placeholder. We do not yet know what the value is, but we want to kind of describe this computational graph. And in the second step, what we're going to do is we're going to say v2 equals tf exponential v1. That's going to create this computational graph node. Then I'm going to do v3 equals v2 plus 1. That's going to create a v3 node. Finally, v4 equals v2 times v3, and that's going to create my v4 node in here. Up until now, no computation have yet happened. All these coding here simply construct the computational graph on the left-hand side. And if you want to ask what is the value of v1 or what is the value of v2, the answer is we don't know. We don't yet know, right? Because the API only start to construct this computational graph, and that's it. So in order to really go and execute, we want to ask what is the value of v4 if v1 is 1. What you need to do is you need to create a session that helps you to send the execution command onto. And then you're going to say session.run v4, saying that, hey, I'm interested in value of v4. And there's a feed dict that tells the system, okay, the value of v1 here should be 1. And then after you run this session, you will get the value of v4 back in here. Okay. So you can find in this API, it's a typical way of what we call a declarative programming. So what does declarative programming mean? So it means that it tries to declare the computation, right? In this case, it first declares the computation that we want in here. And then we have a second execution part that takes that declarations and go ahead and send the declarations onto the system. So let's pause a bit and think about, why does TensorFlow design API in this way? Right? What are the advantages of this kind of declarative API? And also remember that this is API designed by Google, and Google is very well known for designing scalable systems. So there must be some considerations that comes into designing the neural network APIs in this way, right? So if we pause a bit, I think about what are the advantages of this declarative programming API. The few things you might notice. The first thing is that in this code, there's a very clear separation that you have a declaration part that declares the complete entire computational graph, and you have a run part in here. So one of the advantages is that when we go and execute the computations, we kind of know the entire computational graph already, right? So we can do certain kind of optimization. So imagine that in here, let's say I declare this computational graph. Instead of saying, hey, I'm interested in getting a value of v4, what if I'm saying that I don't interested in v4, I'm only interested in v3? What's going to happen is that the underlying system can go and analyze, okay, you have a declaration that contains all the computation graphs, but you are only interested in v3 but not v4. So how about let's go and only execute this part of computation graphs instead of all the components, right? So it gives you opportunity to look at a computational graph and skip some of the computation that are unnecessary. And it does happen. For example, if you have a forward computational graph and you take gradient with respect to that, imagine that you're only interested in gradient values, but not interested in, say, computing the loss function values. Actually, you can skip the loss function computation in a lot of cases. Another advantage of this is that effectively having a complete computational graph gives you a lot of opportunities for optimization. Another thing that you might notice that that's the creation of tf.session here. And that program model effectively means that the place where you run this computational graph does not have to be on the same local machine that runs this Python code. And you can kind of imagine why why this design is being brought up by Google, right? Because in Google it's really important for them to be able to have the scalable computations and also being able to have the execution part, say on a different machine or on a more powerful machine, while we can do some of the developments on a local laptop. So that was like one of the considerations. Imagine I have a local laptop that don't even come with a GPU, and I have a remote session that contains a GPU. What you can do is you can go ahead and send the data to the remote. There's a remote executor that really go and run the computational graph, and then it gives you the computational graph result back in value form. So this complete declarations and separation of the computational graph from the current interactive host APIs kind of helps in that perspective, right? It helps you to be able to organically send values to a different place where real execution happening, but you still do some of a lightweight debugging and other things on your local session. Of course, one of the things we all know is that today TensorFlow will still being widely used, but a lot of people prefer another kind of programming abstraction, which is PyTorch. And let's first take a look at what PyTorch's programming abstraction is, and let's come back and compare this declarative programming abstraction and the PyTorch's programming abstraction. So in PyTorch and Needle as well, we're also adopting this imperative. We're also adopting this programming style. You can find that in order to run these computations, we are simply constructing the code like in here, right? So we'll first declare the needle.tensor, and then you compute exponential function, do a +1, and then you multiply the things together. On one hand, the computational graph on the left-hand side looks similar. So what's happening behind the scene, and what's the difference between this imperative automatic differentiation API versus the declarative computational graph API, is that besides computing the computational graph, when we do V1, we concretely specify this is value 1 here. And and then in the next step, I not only create a computational graph node, but we are also computing exponential V1. Exponential 1 is really hard to compute, but let's imagine the 0, and we will know that this 1 here, right? And for added, it's going to be 2, and at this point, we will know that this is going to be 2 in here. So at each of the timestamp, not only we are constructing a computational graph, but we are also computing the data along the way. And we have introduced the needle implementation as well. We know that in certain cases we are eagerly evaluating that. In other cases, we are using this lazy tensor approach where you don't necessarily have to eagerly evaluate that, but you will be able to lazily evaluate the computations and get the data out. So the difference between this imperative automatic differentiation API, or in other cases called define and run, right? So defined by run. So as you define computations, you also go ahead and running the result. It allows us to execute the computations as we construct the computational graph, and also allows us to easily mixing the Python control flow and the construction at the same time. For example, we could write code like this, right? We can say that if v4.numpy is bigger than 0.5, I'm going to do v5 equals v4 times 2. Otherwise, v5 will equal v4. So you can find that depending on the values of my intermediate computations, we could choose to dynamically construct my computational graph in one way or another. So people also commonly refer to this as a dynamic computational graph construction, as opposed to, in the case of TensorFlow APIs, it's called static computational graph construction. This imperative automatic differentiation API is also not first being brought up by PyTorch. The earlier pioneer here is a framework called Trainer that first introduced this concept defined by run, and it's really PyTorch really take that idea and further develops it, make it and that becomes one of the most widely used deep learning framework today. So let's also pause a bit and try to compare and contrast. Right? What is the difference of this imperative automatic differentiation versus the declarative programming style that we had in TensorFlow? You will find that there are a few things that pops up. First of all, in terms of the optimization opportunities, actually, programming in TensorFlow when possible gives us more opportunity for optimization. For example, if I'm going to go ahead and program our things in this way, effectively, if we're doing eager mode computations, every time if we compute this, we will have to go ahead and really get the value of get this value out, right? So it will miss us opportunities, like for example, in the future, if we look at this entire computational graph, maybe we can fuse those computations together. Because interactive environment, it's really hard to know whether or not this value is going to be referred by another component, right? Also, if we do this and say, hey, I'm only interested in v3, of course, the v4 computation already got executed, right? So you cannot do things like that code eliminations in here. So it really, in terms of like optimization opportunities, the TensorFlow 1.0 API actually is better in a sense. That is why, in a lot of cases, people still prefer TensorFlow 1.0 in production because of the case. And also, if you look at some of the machine learning inference frameworks or deployment frameworks, a lot of deployment frameworks still tries to take this computational graph declaration and execution approach, because that gives them more opportunities for things like memory reuse and other optimization as well. However, why do people still want to use PyTorch's API? This is because, it's much more friendly in certain cases, and it allows more organic mixing of Python, which is what we call host language, as well as underlying computational graph. If you like computational graph, you can view computational graph as another programming language. Effectively, if you look at here, the first component effectively is what we call a TensorFlow programming language that tries to describe the computational graph in here. And then, you can only declare and then run the computation. So imagine that you want to do things like, if v4 is bigger than 0.5, we are going to do one kind of computation, otherwise we're going to do another. In TensorFlow, you have to introduce a special kind of node, like tf.if or tf. There's also loops within the TensorFlow computational graph in order to do some kind of computations, which is a bit cumbersome. Also, in terms of debugging, in a lot of cases, when we go ahead and build neural networks, right, it's not necessarily that you're going to get it right all the time. So it could be very possible that you are going to take v2, and we're going to ask, what's the value of v2? So people commonly will do things like print v2 in here, but at this time point, we do not know what's the value of v2, right? Because you don't even know what's the value of v1 in here. So you know, it's really hard to kind of debug the program in this way. In PyTorch or in an imperative AD APIs, you can directly go ahead and insert a print v2 here, because you know, as we execute to this time point, the value of v2 is already known if I realize the underlying cache. That gives the opportunity to be able to, you know, interact with debug. The ability to mix in the Python code and the computational graph construction is also very helpful. For example, there are advanced models like there's this model called stochastic depth, where you know, in each of the iterations, we're going to randomly flip a coin and trying to construct, you know, neural networks of different depths. And that's really hard to be expressed in a static computational graph construction world, because you know, effectively every time your computational graph is changing, right, depending on the runtime executions of the values. And this happens in things like, for example, natural language processing in some cases, where your computational graph, if you unroll things around a sequence length, it can depend on the number of the length of input. Right? So the flexibility of this imperative automatic differentiation that allows you to organically construct these dynamic computational graphs really gives the researchers much more ability, a bigger amount of ability to be able to express their ideas easily in Python, right? So, and that really leads to the adoption of the framework. So you can find that there's indeed some form of trade-offs between the flexibility and ability to optimize. You know, later there are techniques that try to get even this kind of imperative programming model into a more, you know, efficient state, and there are efforts like compilation, just-in-time compilation, other efforts that help us to move along the way. And so today, if you look at the choices of programming abstractions, you'll find that this imperative automatic differentiation is still being, you know, is being widely preferred in this case. And it's really an interesting combinations of, you know, the ease of use, the ability to be able to express the models that we're interested in, and still being able to leverage underlying acceleration libraries to get the good amount of speed ups. Okay. So until now, we have talked about these programming abstractions. We have studied 3 of them. Caffe, which represents the first generation deep learning framework that allows you to do, you know, forward and backward propagation operations. TensorFlow, that gives you the ability to be able to construct a computational graph and then, you know, execute them, right? Also, we can do like automatic differentiations by extending the computational graph. PyTorch, which gives you the ability to be able to, you know, imperatively compute intermediate computations and dynamically construct a computational graph. It will be useful. We have discussed their pros and cons, but it will be useful for all of us to take a moment and pause a bit and think about what are the pros and cons of each of the programming abstraction. And imagine that, you know, you fly back to the time where in 2013, there's not yet a lot of choices for deep learning frameworks. What kind of interface that you would design to resolve the problem of both modular constructions of models as well as expressing different kind of optimization algorithms and needs? And it would be a very useful thought exercise that I would encourage everybody here to do. Okay, so now we've talked about the high-level programming abstractions. Let's come back and think about, you know, imagine that now we have chosen the imperative automatic differentiation or dynamic computational graph as our programming model, and you know, you have already started to work on Needle as the first part of a framework, as first homework that gives you the ability to be able to construct a tensor, do arithmetic operations among them, as well as composing those tensors, then do automatic differentiation. However, we have not yet talked about how can we construct a neural network from all those tensors. Of course, we can do that using a lowest level API. We can take the tensors, we'll be able to do each of the layers manually, just like what you did for homework 0. However, there are better approaches that we can take in here. And one of the things I want to remind everybody is that, coming back to machine learning, right? When we talk about machine learning, it's not a single cluster of things that you kind of have to take it, and you have to go ahead and implement every part of it. Right? So machine learning itself is very modular. Specifically, every machine learning algorithm at least come with 3 elements. Right? It's a hypothesis class that allows you to be able to take your input and gives you a prediction. There's a loss function that takes the hypothesis, the label, and try to measure how good your prediction is. And finally, there's optimization method that, for a given loss function hypothesis class, it's going to try to find optimized parameters within that space of possible choices. And these you can find at least there are 3 elements that are really independent from each other, right? As we start to develop machine learning libraries, these components are going to translate onto modular component in code that we will be using on composing systems. And this is even true before the age of deep learning. And we can pause a bit and think about how can we translate those modular components onto code. For example, because we have this loss function, right? So certainly there's the possibility of being able to, for machine learning framework, to supply loss functions. And these have been very useful in another framework that I developed before called XGBoost, right? Hopefully some of you also use that framework. There's the ability for us to customize the loss function so that when we first developed XGBoost, we only supported, I think, regression analysis, and there are people that are interested in survival analysis of time series, and they don't have to go ahead and build an entire survival tree boosting package from scratch. They just need to go ahead and customize the loss functions to be able to do that. So that's one advantages of thinking about those modular components. So you can go ahead and change part of your system, hopefully with minor effort, but gives you something that's much more powerful. If you think about the context of deep learning, you'll find that the deep learning is even more modular in the sense that not only they can have these 3 components, hypothesis class, loss function, optimization method, the hypothesis class itself is very modular. So let's take this as an example of, this is what you would typically see in our neural network model, right? So when you go ahead and look at different neural network implementations, sometimes you will see visualizations in this style or in a similar style. So this is a visualization diagram that describes, I would say, depending on how you call it, usually we can call it a 3-layer residual neural network. And it contains 3 residual blocks. So the input goes into first residual block, then feed into second residual block, third one. Finally, it's going to feed a fully connected linear. There's a softmax cross entropy that tries to predict that help us to do like a multi-label classification in a softmax that help us to do like a classification, right, in a softmax cross entropy fashion. And if you look at these diagrams, you do not yet know like what exactly is each of the component correspond to, because when we build a needle library, the only thing we learned is tensors and operation among tensors, but residual block is not a tensor, right? So we want to expand it a bit. Each of the residual block can be composed as by input that get fed onto a linear layer, a ReLU, another linear layer. And the idea of residual block is that not only we want to be able to, do the nonlinear transformation in this pathway, we can also go ahead and directly add input onto, add original input onto this sequence of linear blocks. And this is one of the most important breakthroughs in most important developments in the history of deep learning, right? That help us to build a lot of the deep neural network models, specifically in computer vision. And it's also have other names like highway networks, and and if you look at the recurrent neural network, it's also kind of a similar style where you know LTMs have like a memory cell that memorizes the parsed. So that's a residual block. And if you look at residual block, you can find that still we have those rectangular cells, right? That is not consist of tensors and tensor operations. So we can go ahead and extend them again. So each of a linear layer, in this case, is going to contain an input weight that contains a linear layer. In some cases, a linear layer also comes with a bias term, and in this case, we are simply skipping the bias term to keep things simple. So you have a linear layer that goes into a matmal module, and what we're going to do is we're going to transpose your weight and do matrix multiplication with that input, and that gives you the output in here. And this linear layer also follows the convention like PyTorch and other library uses. Similarly, a ReLU layer will take input, try to take the maximum of input and 0. That gives you output. Okay. So you can find that we can go ahead and expand, right? We can expand every residual module in this diagram, and then expand every linear ReLU in this diagram. And finally, you're going to get a much more deeper, right, in some sense, or a computational graph that contains many more operations. And you can find this recursive decomposition is really modular. And when we are trying to build up your neural networks, we're not thinking in terms of, hey, I want to build it in one matrix multiplication or another. We're thinking about those modular blocks like linear. And then we are composing those modular blocks together using things like residual module, and so on. And this also helps us to think about how we can build our interface design, right? That help us to be able to build up those modules and then compose those modules together. And that's one of the important part to consider when we design interfaces to construct neural networks. If you're interested in learning more about ResNet, there are 2 papers here that you can go ahead and read. And the ResNet paper is arguably one of the most cited paper actually in deep learning as well. So we have talked about this compositional idea, and one of the key data structure here is what we call n.module. In the next lecture, we're also going to implement the n.module. If you have used PyTorch before, you might be familiar with this concept. So effectively, each rectangular block here can be viewed as a module. And this big rectangular block is also a module. So when we design modules, effectively, it's a way for us to be able to compose things recursively together. It follows a common principle called tensor in, tensor out. So the principle says that a module should take, usually, if it's a sequential part, it takes one tensor as input and it output one tensor. In certain cases, it might take 2 tensors, a few tensors, and output tensors as well. The tensor in, tensor out principle really help us to be able to compose things together, right? So if every module takes tensor as input and outputs a tensor, you will be able to take the output tensor and send it to a next module. So it helps you to do computations. There are other things we need to support as a part of the n.module. Specifically, when you look at linear, you can find that we have kind of trainable parameters or weights, right, that are attached to this module. And that means that we want to be able to get, and in order to be able to update the weight in our training procedures, we will need to be able to inspect those modules and get those trainable weight out from those module collections. Of course, we also need to find a way to initialize the parameter here as well. So that's kind of like a module. If you think about loss functions, we can actually view loss functions as a spectral kind of module as well. For example, usually there's a module called softmax clause entropy that gives the hypothesis prediction, the label. It's going to output a scalar value, and tensor of rank 0 can be viewed as scalar value. So it's also output tensors that that can be used to run predictions in here, and it follows what we call tensor in scalar out API convention, right? So you will be able to compose up the modules for getting input prediction, and then you compose that prediction with the loss function label. It gives you a loss function. With this principle, it gives us a bit more composability. For example, if you want to do multiple objective functions, imagine that I want to have a neural network that's able to both gives you bounding boxes as well as classes in that bounding box. That's one instance of multi-object prediction. What you're likely going to have is that you're going to have kind of one objective function module that tries to predict like bounding box closeness, and another objective that predicts the class that measures how good your class predictions are, right? And because we follow the tensor in scalar out principle, so we can apply those two modules and we can just add loss 1 and loss 2 together, maybe in a weighted sum fashion, right? So the ability, we can leverage our we can leverage this modular feature to help us to directly add things together, and then you just call the value dot backward to compute the gradient values. Yeah. There's also another thing that we want to consider is that in certain cases, when you are doing training and when you're doing inference, there might be a slight difference in terms of what kind of operation you want to perform. For example, in case of the loss function measurement, of course, in training, you do want to compute the output loss functions. But in predictions, maybe you don't have to. So usually these modules sometimes come with a training or inference mode, so that allows you to have a slightly different behavior between training and inference here. Okay, that's loss functions. Besides loss function, we still need to be able to, for given neural network models, we want to be able to take in a model and then be able to perform weight updates for them. So for a given model, we want to be able to, and there are implicitly weight attached to each of the modules. We want to be able to first take a list of weight from the model themselves, and then we want to be able to perform updates of those. And this is usually encapsulated in an abstraction called optimizer that takes in a list of weights. Sometimes it also need to keep track of auxiliary states, like for example, momentum in here. So in these cases, right, the optimizer will need to be able to take in the model's query, how many weights are there. So the weights will include W1, W2, W3, and W4, and then it will perform the updates either in some of the rules, right? Either SGD or switch momentum or random updates in here. Another thing that optimizer need to do is we'll need to be able to create and keep track of auxiliary states. For example, the model themselves only come with a weight, but in order to optimize those models, those weights, we will need to create like momentum variables in here. And those momentum variables are being tracked by the optimizers in their internal states as well. Besides the one of the consideration optimizer is that we want to consider regularization factors. In certain cases, for example, maybe we want to think about what is the weight, what is the value of the, we want to apply L2 regularizations, for example, to make sure that the weight value of the each of weight values L2 norm is not too large. So there are two ways that we can incorporate this regularization terms onto a framework. The first way is we can implement it as part of loss function. So you just say loss equals loss plus lambda L2 norm of the weight. So that is certainly possible. And in certain cases, you kind of have to do that because in more complicated gradient calculations, like in certain cases, people might want to be able to compute the L2 norm of the gradient value. In that case, you kind of need to directly do automatic differentiations and incorporate it as part of your weight loss function. Another way is you can simply incorporate as your update rule in optimize update. For example, if I only care about weight L2 regulations, you can directly change your update rule to incorporate what we call weight decay term. That allows us to do this. So effectively, this is a weight decay term that corresponds to the L2 norm regularization that we talk about. This is also very typical in a lot of the optimizers. Besides the weight updates and the optimizers, another thing that we want to think about is how we're going to initialize each of the parameters in our space, right? So the initializations do need to consider, especially we need to consider the order of magnitude of initialization, because if you are building a very deep neural network, if you are initializing the weights to be too small, after few layers propagations, your values will get close to zero. If I'm initializing the value to be too big, then after few layer of propagations, our value will explode, right? It will become very big. So most of neural network libraries come with a set of combo initialization routines that try to control the magnitude of the weight depending on the neural network architecture, so that overall that tries to make sure that your overall magnitude of values do not change very much. And for different kind of weights in your neural networks, like whether it's a bias term that you just add offset to activation value, sometimes you might have running sum of mean and variance that help us to renormalize your neural networks, as well as the weight for like fully connect layers and convolutions. There are different ways for us to initialize them. Usually bias terms can be initialized to 0, for example. Convolution weights and matrix multiplication weight, we usually use uniform distributions or Gaussian distributions, which the order of magnitude depends on the input and output. And usually initialization can be folded in the construction phase of an module. Besides the elements that we talked about so far, one of the important elements that we still need to take care of is the data loading. And so not only want to be able to build a model, we also want to have an effective data loader that feed the model training in an efficient fashion. And there are different ways we can do data loading. For example, in certain cases, we want to be able to pre-process an augment data set by either randomly shuffling the input and transform the input. And different kind of data augmentations can account for a significant portion of prediction accuracy boost actually in deep learning models. So actually, if you look at most of the machine learning training pipelines, the data augmentation is a huge part of it. When people do things like, affine transformations on images, rotating, jittering, to make sure that we get a bigger input space and the model is being robust to those kind of transformations. One of the things that you want to note is that this data loading augmentation is also compositional in nature, right? So we could just singly build a module that simply do random rotation, and then another module that do things like crop and resize in a sequential manner, and we can compose them together to get a more powerful pipeline. So you don't have to design a pipeline that's doing both, right? So you just need to have a single step pipeline that's one or another and composing together to get your end-to-end data pipeline. Okay, so coming back and summarize, we'll find that we have talked about a lot of things in the second part. Talk about module. It helps us to be able to compose up the neural network libraries. We can also talk about module can help us to build the loss functions in here. By passing parameters and gradients to optimizer, we will be able to go ahead and try out different kind of optimization methods. there are different forms of initialization we can do to make sure that the weight values are being initialized correctly. And finally, there are data load and pre-processing steps that help us to load the data and augment the weight and feed it to the training pipeline. And this summary really highlights how modular the deep learning models are, right? So that is really one of the reasons why deep learning kind of dominates a lot of machine learning field, in the sense that the cost of trying out new things is really low, right? So if imagine that I only care about doing detections, the developer and the scientists do not have to go and rebuild the entire ResNet or mobile net from scratch. You can be able to directly use the backbone of ResNet mobile net, put a detection loss function in the end, and then you will get you will be able to experiment the end-to-end pipeline there. So, and if I'm only interested in developing new optimization method, like a variance of Adam for neural network training, we just need to go ahead and replace the optimizer part. So this modular nature is really amazing, that help us to be able to build different deep learning solutions together and also put them together, right? So everything kind of compose well with each other, so that we will be able to customize one part while working together with the rest part to get an end-to-end solution. And that is kind of like one of the secret sauce why deep learning and a lot of deep learning frameworks actually kind of come back and dominates a lot of machine learning. Of course, there could be other modular components that we have not yet covered today, including things like how you can do learning rate schedule. There are components that might help with things like hyperparameter tuning and so on. I would certainly love us to, as an exercise, come back and think about what are the possible modular components other than the things we talk about today. So in the end, I want to come back and revisit the programming abstraction. And now we have talked about the modular components and how we can use different kind of modules, right, to compose up the deep learning acceleration. Let's come back and revisit the abstraction again, and really trying to think and appreciate how this kind of layer-wise composition helps. If you look at the Cafe 1.0 API, you can find that a layer API in here at least couples two things. It couples the gradient computation and module composition. So in order for us to, for example, build a ResNet in here, well, it's kind of a bit complicated because I can go ahead and introduce a residual layer, but then we will need to be able to define a gradient computation for a residual layer, which is kind of non-trivial, right? One of the key observations that we make in Needle and in the second generation framework is that we can separate the gradient computations and module composition in two levels of API. In the case of Needle and PyTorch as well, the computational graph construction and automatic differentiation or gradient computation is being handled by tensors and computational graphs among tensors. However, in order to modulate compose things together, we're introducing this concept of n-dot module. And the module can contain things like a residual module that effectively is more coarse-grained than the lower level tensor level operation. So by separating these two concerns of how we want to be able to compute a gradient and directly relying on the underlying tensor library to do that, we will be able to focus on modular compositions in a much more simpler fashion by simply defining the forward computations of all the intermediate modules, and then use automatic differentiation to handle all the gradient computations. And that actually really helped us to be able to develop more model easily. And this may be obvious now that you have seen the designs, but it's really interesting to come and reflect, how the design decouples things and how this approach helps us to be able to not only do automatic differentiation more effectively, but also composes the modules in a more organic way. Okay, so that is the end of today's lecture. Thanks everybody for coming. In the next lecture, we are going to really get our hands dirty and implement some of the high-level designs we talk about this lecture. I will see you in the next lecture then.